So let's start. I don't know, there are very few people today. 72. Maybe some of them will join. Okay, so we are finally at the last topic of this course, and so the other batch is considerably behind us. We'll have to give them some time. But the next week will be just sort of revision. Like if you haven't understood anything or you want me to go over it again, you have to inform me before the class. Then we can probably discuss this. But technically, this is the last lecture. Okay. Okay. So we have seen plenty of approximation algorithms. Now we'll see one more, which is the weighted vertex cover problem. So I briefly introduced this to you in the last class. So what is, you all know what vertex cover is, right? So this is just a weighted version of it where every vertex is having some weight. Okay. And so you are given a graph, set of vertices, set of edges, and each vertex is having some weight, non-negative weight. Okay. WV. Okay. And now we want to find a vertex cover such that this weight is the total sum of the vertices. We are picking some subset of the vertices, and we want the total weight of all these vertices to be as small as possible. Okay. So if you recall, the unweighted version where there were no weights, right? We just needed to pick the minimum vertex cover. So the way we proceeded was we picked a set of edges which don't share any endpoint, and pick the maximum set of such edges and just put both the vertices of those edges in our vertex cover, and that way we claim that it will be a 2 approximation, right? Now, when there are weights on the vertices, how will we proceed? That's the main question. Because here, one particular vertex cover can be better than the other because of all these weights. We don't know what these weights are. They could be any non-negative values. Right? So somehow you want to take these weights into account. And a minimum size vertex cover may not always be a minimum weight vertex cover. Right? Because there might be a larger vertex cover, but whose total weight is small. Okay. So how do we proceed here? Any idea? Yeah, so there is one answer which is find all vertex cover and see their weights. If only it were that easy. So, in fact, minimum size vertex cover is also very difficult to find, as we have already seen in this course. The thing is, we don't know how to find the minimum size vertex cover. And okay, so can I repeat the question? Sure. So, given a graph, you are given this graph G, vertices and edges, right? And every vertex is having some weight. So, normally we give weights to the edges. In this case, we are giving weights to the vertices. Okay. And now I want to find some vertex cover, right? You know vertex cover, right? You want to find a set of vertices such that every edge has at least one vertex in this set as endpoint. Okay. And you want the total weight of the vertices in this vertex cover to be minimum possible, right? As small as possible. So is the question clear? Okay. So let me give you an example. Maybe it is easier to look at it that way. Yeah. Let's say, yeah, like these are the weights given 3, 5, 3, 4. And so, how are we going to find this vertex curve? So, what is the optimal vertex cover here? 4 and 5, is it? Yeah, 4 and 5. The total sum is 9. And yeah, again, find all possible vertex cover. So, that's the thing that finding a vertex cover is very hard. All possible. Even finding the minimum vertex cover is extremely hard. Uh, it is NP complete. Right? So that obvious strategies work. To each edge, we can assign a weight equal to half the sum of the weights of the joining vertices. Okay. And find the minimum spanning tree. Oh, that's an interesting idea. So what is it saying? So each edge, so this edge will get weight 3.5, this edge will get weight 4, this will get 4, 4.5 and 3.5. And now I have to find some minimum spanning tree here. Okay. So let's say I pick this 3.5 weight edge. The set of vertices of tree. No, but in minimum spanning tree, the set of vertices is all the vertices, right? So are you going to pick all your vertices as vertex cover? Surely you can do better than picking all the vertices. Okay. Uh, sum of the weight, take the sum of the weight of the edges of the tree. That will be the weight of your vertex cover. Uh, okay. So what's the sum of the weight of the edges of the tree? So I can take this 3.5. I can take this 3.5 and maybe I'll take this 4. Okay, so the total is 11. Okay. Yeah, the best is 9, 4 and 5. Another best is 3, 3 and 4. But there is no vertex cover with total weight 11. Is there? Yeah, I don't see how you will get a sum of 11 using this weights. Okay, so one more idea. We have sort the vertices in ascending order with respect to their weight. Then traverse through all the vertices and make all the edges which is connected to that vertex as visible. Okay. Repeat this for all the vertices. Yeah, that is a very natural strategy that you take the vertices in increasing order of their weights. So here we are going to pick 3 and cover these 2 edges. We pick another 3, cover these 2 edges. But then this center line still remains uncovered. So you are going to pick 4. Okay. So at least we get to 10. Uh, how are we going to get 4 and 5? 9. We need to repeat it until all edges are not visible. So you mean all edges are visible? Yeah, so that's what I've done, right? I pick this 3, pick this 3, and then you have to pick this 4 because this edge 4 to 5 is not visible. Okay. So yeah, the main problem with this is it's not necessary that the highest weight vertex is not there in the vertex curve. Right? In this example, we have seen that 4 and 5 are a vertex cover, and 5 is the highest weight. Okay. So then there is one more idea. So he's saying make two lists. Okay. One is 4 comma 3, 3 comma 2. What is 2? Weight of total edges connected to that. Then second list of relative edges like max of 5, 4. Oh, where is 2? I don't understand that. Should choose the vertex with more joined edges and less relative edges. Okay. Okay, we have one more. Select the vertex such that weight of vertex divided by number of edges incident to it is minimum. This makes more sense. Then delete the vertex and edges incident to it from graph and repeat this till the set of edges becomes empty. Okay, let's see what this guy is saying. So he wants to select the vertex such that weight of vertex divided by number of edges is as small as possible. Okay. So what's happening here? So this vertex will have weight uh, 3 divided by 2. Right? There are two edges. Similarly, this vertex will have weight 3 divided by 2. Both are 1.5. This will have weight 4 divided by 3. Okay, 1.33. And this will have weight 5 divided by 3. So we'll get some 1.66. Okay, so you'll pick 4 first because that was the smallest. Then you are going to pick one of these 3 because that was the next smallest. And then another 3. Okay. Yeah. So we are again in the 10 case. Okay. So one more idea. We can use a greedy strategy. Uh, Algorithm starts at the vertex. Okay, the same thing. Weight divided by number of edges not already covered is minimum. Okay, so it starts at the vertex whose weight divided by number of edges is minimum. Fine. So it is 4 divided by 3. So we'll pick this vertex 4. Okay. And now the next how is computing. Uh, the ratio of weight divided by number of edges not already covered. Okay. So this thing will have 3 divided by 1, and so both the 3 weight vertices will have weight 3, and this thing will have 5 divided by 2. That is very, very interesting. Okay, so that's the way we get 4 and 5. Okay, great. So we have at least something which gives the optimal solution. At the starting point of the edges for the initial vertex are that those covered by the vertex. Uh, Sorry, I don't understand. At the starting point? Okay, the edges are for that covered by the vertex. Mhm. Yeah, I understood your algorithm. It also gives the optimal solution for this case. Right?
No, sir.
Yeah.
Sir, here three was not covered by the three vertices, na?
Uh, 3 was not covered by which vertex?
Means three not covered 4, 5, 4, 3, and 3, 5.
4, 5, and yeah, it is covering all the edges. Right?
Means 3 is only covered 3, 5 or 4, 3.
3 is only covered by 3, 5 and
If we consider
4, 3.
if we consider only 1, 3 vertices, if both
Okay. No, we want to cover all the edges.
no sir means
Right?
uh, we can here in this algorithm we consider 3 as both 3 both combinedly or separately.
Separately, these are two separate vertices.
Okay, means sir, if a number of
Sorry.
vertices upon uncovered edges, then 3 by
Hmm.
3 was come na.
Okay, so let's go over it again. So first we pick the vertex whose weight divided by number of edges is as small as possible, right? So this will be 3 divided by 2 because there are 2 edges incident. Okay. This will be 4 divided by 3 because there are 3 edges incident. And this will be 5 divided by 3, right? So what is the smallest among all of these? 3 divided by 2 is some 1.5 and 4 divided by 3 is some 1.33. Right? That is why we pick this vertex 4. Okay. Now in the next step, we look at its weight divided by the uncovered edges. Okay. So what is uncovered by 3? Only this particular edge, 3 to 5. Right. So this 3 divided by 1. Similarly, for this vertex 3, only this edge is uncovered, but 5 is covering both of these. Right? So it will be 5 divided by 2. That comes out to be 2.5.
Means sir, 3 was covering only 2 vertices. Na 4 or 5 was also not covered by 3. Edge 4, 5 was also not covered by 3.
Yeah, sure. But 4 was initially covering all these 3 edges.
Okay, means after covering after 4, how much was remaining? We considered that.
Yeah, we considered
Okay, sir.
that. So 3 was covering only 1. This 3 was also covering only 1, but 5 was covering both.
Okay, sir.
Okay. Yeah, now the big question is, will this work for all possible cases? Okay, so how good an approximation it is giving you. So how are you going to analyze this particular algorithm? Yeah, so there is one more solution which is really the same thing. Uh, yeah. Now we want to give a good approximation guarantee. How does it compare with the optimal solution? In this case, we are getting the optimal solution, but in general, we may not. Can you claim something like it is at most twice the optimal solution? That is in fact more difficult part because yeah, approximation algorithms are generally very easy to design, and yeah, many of you have come with some interesting approaches. But the more difficult part is analyzing the approximation factor. Okay, how are you going to say that it is at most some constant times the optimal solution? Okay, so I will tell you what algorithm I have, which is a different technique, but it is more general. Okay, so you can use this technique in many different problems. It's known as the pricing technique. Okay, uh, so what I'm going to do is I will assign a price to every edge. Okay, so let's call WV is the cost of using V. Okay, so it's the weight of every vertex, and PE is the price that E pays. Okay, this is just some notation which I'm introducing, and I want to maintain this invariant. Okay, so the sum of the edges incident to V, the sum of the prices of those edges is at most the weight of that vertex. Okay. So we have seen a similar strategy during Prim's algorithm for minimum spanning tree, right? So we initially assigned the weights to be 0 and then we gradually increased them so that a certain invariant was maintained. So summation of PE is less than equal to WV. Okay, so the edges adjacent to V don't have to pay more than the cost of. Okay, so instead of vertices, now we have gone to the edges and we are assigning these weights to the edges. Okay, so let's say there is this weight vertex V with weight WV, and these are the edges incident to it: E1, E2, E3, E4, E5, and P1, P2, P3, P4, P5. The prices of those edges. Okay. So now what we are saying is, suppose that we have a graph VE such that C is a vertex cover, right? So now if PE is the fair price for each edge, then it is the case that some of the prices of these edges is at most the weight of our vertex cover. Okay. So can you see this? Right. So this was the definition we were starting with. Summation of prices of the edges incident to is at most the weight of the vertex. Okay. And now we are saying that the sum of the prices of the edges is at most, all the edges is at most the weight of the vertex cover. Right? Why is this true? Is because every vertex in the vertex cover is covering some or the other edges. Right? And finally, it is covering the set of all edges. But when you are computing this weight, you might include some edge twice, right? Because two vertices may cover the same edge, and therefore Since we are covering all the edges, the sum of the prices of these edges is at most the weight of that vertex. Correct? Yeah, there is one question. Yeah, Greece. Okay. Okay, so there is just one more notational thing which I want to introduce. We say that a vertex V is tight if the sum of the prices of the edges is incident to it equal to W1. Okay. Because we have this condition now that summation of the prices of the edges is at most the weight of vertex. Okay. And now we are saying that a vertex is tight if this is equal to. Okay. So the sum of the prices of the edges is equal to the weight of the vertex. Okay. And finally, we are going to check which vertices are tight, and then if that vertex is tight, we will include that in our vertex curve. So we start with the small prices of edges, and we are gradually going to increase these prices so that certain vertices become tight, and those vertices we are going to add for final vertex curve. Okay. So just to make it clear, this is my algorithm. Okay. So for each edge, initially I will set its price to 0. Okay. And then I will gradually increase the price for the edges in a fair manner as long as possible so that certain vertices become tight, right? So the sum of the prices of those edges uh, is the weight of that vertex. And finally, I'll return the set of those tight points. Okay. Okay, so let's see how it works for this particular case. Okay, maybe there is a question. Okay, yeah. So how are we going to do it for this particular special case? Okay. So initially we set the weights, prices of all these edges to be 0. Okay, and then we are going to gradually increase whatever the prices of these edges. Okay. So let's say we pick this 3 and 4. Okay. So we'll increase the price to 3. Okay. So what is happening? Now this weight we will decrease to 0. So we will reduce the price from the weight of each vertex. That means we can't add any more weights to edges incident with this. Okay. So that is sort of capturing vertex cover, right? Because once you have taken this vertex, uh, you can't, you don't have to cover this particular edge again. So that is why we are just assigning its weight to 0. Okay. So initially, we increase this price to 3 and decrease this weight to 0, and this weight also decreases to 1. Okay. So now we'll work on this new graph. Now what are we going to do? Right? Let's take this edge 1, 2, 3. Now we can increase the price to 1 here. So this weight becomes 0 and this particular weight becomes 2. Okay. So that means we can't assign any weight to this edge, right? Because this particular weight is 0. And similarly, we will take this particular edge, we will assign its price to be the minimum of these two. And let's say we assign this price of 2. Now 3 is remaining. So this again becomes 0 and this becomes 3. So now all the vertices have weight 0 except one vertex. Then we can't increase the price of any other vertex. So that will be our final vertex. Okay. So there is a question. Yeah. And finally, the 0 weight vertices we are going to include in our vertex cover. Yeah. So is the algorithm clear what we are doing here? Right. So we are gradually increasing the price to the maximum possible. So when we are increasing the price, it has to be the minimum weight of one of the incident vertices. And this you keep on repeating. This is well known as the pricing technique. Uh, so initially we set these prices to 0, then we saw that 3 and 4, the minimum is 3, and then update the weights of these vertices by removing the price of the incident. So this weight becomes 0, this weight becomes 1, and then we pick this particular edge 1 and 3. So the minimum is 1, so we can assign this as price as 1, and again update this weight to 0, and this weight becomes 2. Okay. Then again we pick the minimum, so the minimum is 2, so the weight becomes 0 and 3, and finally we can't do it, right? Because now all these weights are 0, so we can't increase the price of any edge anymore. So these are our vertex curve. Okay. The algorithm is correct. So, or do you want to say that C is a vertex cover? Right? Why is C a vertex cover? It is because we are covering all the edges, right? So you can't increase the price of any edge anymore. That means we are covering all the edges, right? Because that's the point where we stop, when you can't increase the price of the edges. So assume that some edge was uncovered by this particular pricing strategy. That means that both its endpoints have some non-zero weight. Okay? And then we could have increased the weight and cover those particular edges, right? Because we are only including the vertices with 0 weight at the end of our algorithm. If there was some edge which was uncovered, that means it had some non-zero weight, and then we could have increased the price of that edge. Okay. The algorithm is certainly correct that C is a vertex cover. The algorithm also takes polynomial time, right? Because every time we are traversing some edge and updating the widths of the thread. It's kind of a greedy strategy. Okay. So almost all approximation algorithms are greedy. Somehow greedy is the thing which works here. And the last thing we want to say is that it is a two approximation. Okay. So how are we going to say that it is a two approximation? In the case when there is a vertex whose original weight is 0, that time the covering of edge adjacent to that vertex is not guaranteed. Why do you say that? So because zero weight vertex, it doesn't affect us, right? And whether we'll always include that vertex, let's say. We'll always include zero weight vertex. Okay. There is no difference in the final weight anyway. Yeah. So okay. I hope this algorithm is clear. So because that's what we are doing. Whatever zero weight vertex are remaining, we are gradually reducing these weights to zero, and whatever zero vertex are there, just pick it in your vertex. Okay. Now, of course, we need to prove that it is a true approximation, right? So we know that algorithm is correct. It returns some vertex cover and it takes polynomial time. And what we want is we want to claim it is a true approximation. Right? So why is it giving me a twice the optimal solution? Okay. So this pricing technique is very general. It's not just for this weighted vertex cover problem. You can apply it to many other problems as well, where you want to minimize the weight of something. Okay. So that is why I can use this. Okay. So I hope the algorithm is clear. And now we need to see y zeta 2 approximation. Yeah. So what are we doing here? That's the main thing. We are looking at the prices of these edges. Okay, is there a question? Yeah, no. There's no question. Okay, so yeah, now what are we doing here? We are looking at the sum of the prices of these edges. because we updated this thing and we know that it is at most the weight of the vertex. Right? So the sum of the prices of the edges incident with a particular vertex is at most the weight of that vertex. Okay. Let me open another PDF. I have this. Okay, so this is how we are doing things. Okay, so we'll look at the sum of the prices of these edges. Okay, so what is a natural upper bound on that? Let S be my vertex cover. Okay, so I'll take every vertex in my vertex cover and sum of the prices of the edges of those in my vertex cover, right? Because this vertex cover is covering every possible edge. Okay, so if I just take the edges incident with a vertex in the vertex cover, that is going to obviously cover all edges. Okay, it might be possible that two different vertices are covering the same edge, and that is why we have a less than or equal. Okay. And what we said that the sum of the prices incident with a vertex is at most the weight of that particular vertex. Okay. So this is one thing which we know that summation E belonging to E price of E is at most the weight of S, where S is any vertex cover. Okay. So it might be any vertex cover, might be the optimal one, suboptimal one, but the sum of the prices of these edges is at most the weight of that vertex cover. Okay. And what follows in the remaining is that we'll just use this fact that summation of prices of these edges is at most this thing, right? So you take any vertex in the vertex cover and look at the prices of the edges which are incident, right? And that is going to be at most the sum of the prices of the edges incident with any vertex because S is a strict subset of V and S is a vertex cover, right? Okay. And now, how do I interpret this thing? Right? So it is equal to in every edge, every vertex is appearing twice. Right? There are two different vertices appearing here. Uh, so because you can write this as I comma j or j comma I. It's one and the same. It is twice the sum of the prices of the edges, which is at most twice the weight of the dimmable vertex. Okay. So turns out that it is a two approximation. Yeah. Okay. Any questions? Okay, last inequality. Right, so we are just applying this thing. Summation of the prices of the edges for every edge is at most the weight of S, right? Uh, so twice the summation of edges, the prices of the edges is at most twice the weight of S for any vertex cover S. Right? So I could pick any vertex cover. So I'm just picking the optimal vertex cover here. So at most twice the weight of S star. S star is the optimal vertex cover. Okay. That's clear because finally what we are looking at is this particular thing that we are looking at the sum of the prices of the vertices in our vertex cover. And what we have shown that it is at least the sum of the prices of the edges, which is just the weight of S, and it is at most twice the weight of the optimal vertex cover. Right? So you have to use this first statement here. Because in the first statement, there was nothing special about this S. Right? We are arguing for any particular S. Can you please take some more examples of how to calculate the approximation ratio? Yeah, sure. I don't have any problem. Okay, then we'll see some more approximation examples. Yeah, more than design, it is an important skill to know how to compute the approximation factor. Okay. So I'll maybe take some more examples of problems and teach you how to compute this approximation factor. Uh, yeah, so there is a question. Is the S in the first inequality any vertex cover or is it the vertex cover outputted? No, it is any vertex cover. Any vertex. Okay. So it's a general statement. I take any vertex cover, it is covering all the edges. So it is at most the sum of the prices of the edges. And at most the weight of these vertices. Okay. Okay, so we'll see again in the next class. Uh, right now, some of you are having difficulty in grasping this. Okay. Okay, so we'll meet on Monday. We'll see some more examples of uh, approximation algorithms, and then it will be the end of the course. Sure. Okay.